Well, hello everyone, and welcome back to this introductory course on database management systems and SQL. Today, this is the 7th video in the series, and we will be looking at some of the advanced concepts now. We'll be looking into aggregates and schema refinement in database design. So before we get started, a quick reminder that this course is brought to you by Newton School's Launchpad initiative. So the link to Newton School's website will be given in the description section. So please do feel free to check that out. Right, we'll get started. Yeah, sorry about the technical difficulties. We will get started shortly. So yeah, as I was saying that you can log in. That the Newton School's website link will be given in the description section. So please feel free to check that out. And once you're here, you can log in or sign up depending on whether you are a new user or a returning one. Once you have signed up, you can sign up or register for the course from Newton School website itself. The advantage that you get by signing up for the course from Newton School is that along with the video lectures, you also get to see assignments. You also get to do daily quizzes. And once you have completed all the videos, you are eligible for a certificate. Also, you will be eligible for a doubt clearance session if you register for the course from Newton School site. So for registering the course, come to the dashboard after you have signed in. Under the Launchpad tracks, look for the course, the Complete Database Management and SQL course for beginners. Once you have found the course, click on apply for that particular time, and then that course will start appearing in your tracks, and then you can resume and start the course anytime you want. All right. Now let us get started with the actual content of today's lecture. So as we said that we'll be doing initially some of the advanced SQL queries, and then we will look at schema refinement. So first, looking into the aggregates. So till now, whatever queries that we're doing, we were not really doing any mathematical operation on the results that we were getting. That is, we're doing a lot of filtering, we're doing a lot of projection. Then we were joining a lot of tables, doing some projections and filtering on them. So we saw some complicated scenarios there. However, whatever results that we were getting, we were just showing those results as a list of rows to the user. We were not doing any sort of mathematical operation on these on the data that we are getting. To take an example, to see an example, what exactly I mean by such mathematical operations. So we know that in the tables that we were following, we have got a table where we call students, where we can see the CGPA that each and every student has received. Now, what if I have a situation where I want to calculate what is the average CGPA that all the students are receiving? So in that situation, I'm not really asking, or I'm not really writing a query to get a list of data, but rather I'm writing a query where I'm going to get a list of data, and on that list of data, I'm going to do some sort of a mathematical operation and then show that result back to the user. So that is what is known as an the aggregate function, where instead of getting a single row or a multiple rows, we are getting those rows and we're doing some sort of an aggregate mathematical function on top of it, and then giving the result back to the user. So some of the aggregate functions that we have are called sum. So sum is used to sum certain values. Count is used to simply count the number of rows that you have returned. Average, as it sounds, it is used to calculate the average of some particular values. A max and min, as they sound, max is used for calculating the maximum of particular values, and minimum for calculating the minimum of some of the values. Now the aggregate functions which are shown here on the slide, they are not mutually exhaustive. That means there are a lot of other aggregate functions out there as well which can be used. Like you have got advanced statistical functions like standard deviation, variation, percentiles. All of them are supported by SQL, and based on the version of SQL you are using and the vendor that you are using, the syntax might differ a little bit, but the logic and the concept remains same behind all the versions of SQL. Okay. We will go ahead and try to do some practicals so that the understanding is better. So for our practicals, as always, we will be using Newton School's SQL editor. So we already had this data created for us, so we will not spend time in creating the data once more or creating the schema and the tables one more. So just a quick revision of the data that we have. So we have a department table and the student table. Department table holds the department information and the student table holds the student information. The student table has got a foreign key called department ID, which references a department table, and this is used so that we can see which the student belongs to which particular department. There are two other tables that we have. One is the course table. So the course table contains the details of each course or subject, and that also has got a foreign key reference to department. And then there is a bridge table between the student table and the course table, which tells us which student has taken which courses. Okay. So this is how the student structure, this is how what our structure is. So we will try to do all our aggregate functions initially on the student table. So in the student table, CGPA is a numeric value. So this is probably a very good example, or it's probably a very good attribute where we can try to do some of this aggregate operations. So let us go ahead and try that. So the first one that we're going to be doing is we're going to be calculating the maximum value. So before we calculate the maximum value, let us just take a look into the student data, and we will do an order by. We'll just order by the records that we have there in the descending order by the CGPA, just to see what is the highest CGPA that is recorded. So the highest CGPA that is recorded in this table is 9.48 given by the student Project B. And the lowest CGPA that is recorded in the table is 6.5 received by the student Vishal Kumar. Okay. Now this is where we have got all the, this is the traditional query that we are writing, where we are getting back all the records. Now, what if I want to do some aggregate functions on it? And the first aggregate function, let us say I'll be doing is calculating what is the maximum CGPA that has been recorded for this particular student table. So for that, the query is simple max, and then you need to pass in the max function. This is an max is an aggregate function. So in the max aggregate function, you need to pass on which attribute present in the table do you want to apply that aggregate function. So here I want to apply that on the CGPA attributes. I do write that select max CGPA from student, and I don't need the order by anymore really. So now if I go ahead and execute it, my answer should be 9.48. And there it is, the answer is 9.48. And similarly, I can do min as well. So I'll do min CGPA as well. So min is again an aggregate function, and to this aggregate function, we are passing the attribute that is CGPA attribute. So this aggregation will happen on the CGPA, and I'm going to get back the minimum CGPA. Now here, since I'm doing max CGPA, comma min CGPA, I'm going to get two records here. Let's try that. Yeah, I'm going to get 9.48 and 6.5, and we saw earlier, right, that 6.5 was the lowest CGPA that was recorded. Let us do some other kind of aggregates. We'll do average as it sounds that here average is simply going to return back what is the average CGPA that we have, which is 8.21. So again, like I'm not doing the calculation, but we can trust SQL on this, that they are doing the proper calculations. Okay. While we're doing the maximum, the CGPA, one more thing that we can do is we can still apply some where clauses. So what where clauses are going to do is that is it is going to filter out the number of rows that we have, right? Like for example, let us say that I want to like select all the female students. So let's say I do something like this. All right, sorry. If we do this, this query is actually simply going to give us back all the female students, and it is going to give us back who's the highest pointer and who's the lowest, who has received the lowest pointer. So here you can see this student with the 9.24 is the highest pointer, and this another student has got the lowest pointer with 7.4. Now, if I want to apply aggregate here, I can do that as well. So all I need to do is maximum of, let's say, CGPA, and I'm going to get the minimum of CGPA as well. And if I go ahead and apply this, yeah, so here you go, 9.24 and 7.4. So what I really wanted to show here was that when you are applying the aggregate function, you can still use where there. And what where is going to do is where is simply going to limit the number of rows that is being written. And based on the number of rows that is being written, on top of that, I'm doing the aggregate function. So in the earlier examples, I was doing the aggregate function on the entire table itself, but here I'm restricting the number of rows. I'm restricting the number of that is in the result. I'm restricting the number of rows, and based on that, based on the result that I have received, I'm doing the aggregation on top of it. So that is another example of doing it. Now let us take another query. So let's say the query right now is that I want to receive the names and the other information of all the students who has received a CGPA above than the class average. So For that, let us try to first find out what is the average CGPA. So the average CGPA is 8.21. So now my query is that, hey, I want to find out the names and details of all the students who has received more than the average CGPA of the class. So I know that the average CGPA is 8.21. So I can then do something like this, right? That select star, let's say, from student where CGPA is greater than 8.21. So it's greater than equal to actually 8.21. Now, if I go ahead and execute this, what is going to happen? So first I'm going to get the, sorry, again, so the semicolon is actually important, because if you do not give the semicolon, then SQL doesn't treat it as an end of statement. So but if I don't give a semicolon, I start writing another select statement. SQL thinks both of them are same statements, and that's where compilation error is thrown. Anyway, carrying on. So 8.21 was average CGPA, and then I'm seeing that these all students have received a CGPA of above 8.21. So you can see 9.1, 9.14, 9.24, 8.6, and stuff like that. So this is one of the queries where we are trying to see that how many students who has received above average CGPA. But now there is a small problem here, or rather it's not a small problem, it's actually a pretty big problem. So the problem is that this query that I've written, it is not at all dynamic in nature. That is, I'm first writing on one query which is going to give me the average CGPA of the entire class, and then I'm trying to write another query which is going to use the value returned by the previous query and then hard code it here. So at any point of time, if there is a question or if there is a query that, hey, I want to find out the students who has received more than the average CGPA, I'll always need to write two queries. First, I need to write a query to find out what is the average CGPA, and after I found that out, then I have to write another query by inserting the dynamic value that, hey, this is the value, so this is the answer that we're going to get. So this is not dynamic in nature. You have to do it in two shots, and also this is very risky in nature, because like if you hard code this data, that is 8.21, we know is the average CGPA. If I hard code this data and I say that, hey, this is the query which is going to be which will always return back the average, which will always return back the number of students who has received more than the average CGPA. When after each semester, when the CGPA of the students changes, I will always need to go back and change this value, this 8.21. To get this value 8.21, I'll always need to run this query and then get this value. So this is not really a very user-friendly way, or this is not really a very developer-centric way of getting the stuff done. Ideally, we should be getting it in a single shot, in a single way, that in a single query itself, I should be able to get that value. So now the question is, how do I do that? So it's actually pretty simple. It is actually pretty intuitive once you see it. So you see this value, that is select this query, select average CGPA from student, it is already giving back a singular value, that is 8.21. That what is the current average CGPA of all the students. Now what our problem is, that is in this portion where we have hard coded the value, of the average CGPA, I just need to make it dynamic. That is, whatever result I am getting here, I simply need to do that calculation here itself. That is, instead of writing 8.21 here, if I could have written this exact statement, which is actually calculating the average of the student, I can easily do it. Let's see how. So here, if I just do select, or I'm just going to go ahead and copy this statement because I don't want to write it. Add in one line. Let me execute this. So there it is. I'm getting the same result, and here I don't have to do it in two queries. One single query is going to do it. But although this one single query is actually nested in nature, these are known as nested queries, because there is one query within another query. But still, here I do not have to do any hard coding. I do not have to hard code the value of the average. I can calculate the value of the average dynamically from the student table, and then use that value in the query itself. So one question, or rather one thing to note here is that if you're trying to do something like this, that where CGPA is greater than some value, and in that some value you're actually writing a query, you need to ensure that your query returns back only one value, because you're doing a singular value to a singular value comparison, right? Because CGPA is a singular value, it's an atomic value, it's a double. And whatever your query returns, that also must be then atomic in nature. That also must be like a singular value in nature. If instead of returning a singular value, if this guy was returning a table, then there would have been a problem. That is, instead of returning one column, had I been returning two columns, then it would have written me a table, right? And that is a complex data type. That is not a simple or a singular data type. That's a complicated data type. So now if I try to compare a single or an atomic data type with a complicated data type, there could be multiple issues. There could be processing error, there could be runtime error and stuff like that. So that's why when you're trying to write a query like this, you need to ensure that your LHS and your RHS, that is your left hand side and your right hand side, both of them are of the same data type. And generally we try to keep it atomic in nature. So we need to ensure that both your left hand side, which is CGPA, is atomic in nature, as well as the query that you're writing here should also be atomic in nature. That it should give you back a single value. All right. We'll take one more use case of, let's say, count. So count is simply used to give you back that, okay, whatever result I'm getting, the count is going to only tell you, okay, how many records that you have received. So let's say this same query, if I modify this a little bit and I say that I don't want to know the names of the students who has received more than the average, rather I want to know how many students have received above average and how many students have received below average. So here, instead of select star, which is actually going to give me back all the rows, I just want to know how many rows I'm getting. And for that, the aggregate function that we should use is count. And what is the parameter that we can pass here? For now, I can simply pass star, but I could have also passed something like simple CGPA or simple or any of the attributes I could have passed. But for now, let me just pass star. Star means it is going to calculate and tell you, okay, how many records or how many rows I have got. So here, if you calculate, I've got 1, 2, 3, 4. So 4 records have been returned. So if I execute this query, my answer should ideally be 4. And there it is. And if I want the reverse one, that is, I want to find out, okay, how many students have received lesser than the CGPA, lesser than the average CGPA, go ahead and do this. So I have, I think, 12 students. So yeah, 4 minus 12 is 8. So 8 students have received below average marks and 4 students have received above average marks. So that is exactly what count does. That is, from whatever table you are getting the data from and whatever filter you are applying, the number of rows that you have got, it simply counts the number of rows and gives it back to you. This is actually very important when you're trying to build something like a pagination system. So a few videos earlier, we had seen that how to do pagination. That is how we can, get like, let's say there are 100 records, but you don't want 100 records. You want the first 10 records, then the next 10 records, then the next 10 records and stuff like that. So if you're building a system like that, a lot of time upfront, you need to know how many total records are there, because based on that, you're going to be writing some UI logic, right? So after you know how many total number of records are there, then you can get the top 10 records, then the next 10 records and stuff like that in an incremental order. So in that situation also, count becomes very important, where first we are going to trigger a query to get how many records are there, and then we're going to slowly we are going to be fetching the records one at a time. All right, so that is about the aggregate functions. So these are the aggregate functions that we will be doing. So before I move on to the next topic, I just to take a look into the live chat to see whether there are any questions. No, I do not see any questions on this. That's fine. So just a quick reminder to everyone that if there are any doubts or if there are any questions, please put them in the live chat. In case you are seeing a highlight of the video, that is, you are not live, you can post your questions in the comment section. Or if you have registered for the course from Newton School, you can post your questions in the discussion forum as well. All right. Okay, I will move on. So we are done with the aggregate function. The next thing that we're going to be doing is schema refinement. So before we do schema refinement, just a quick reminder of what exactly our database design process was. So our database design process, which we did in the second video. So if you want a quick recap, you can go ahead and take a look into that video. So database design actually tells you about certain processes that you need to do for actually doing a complete database designing. So first one was requirement analysis, where you are going to be just analyzing what is the kind of software you need to build. So what kind of data that you have, what kind of rules that you have. Second, you are going to be building a conceptual model. So we saw that we can use something like the ER model to find out what are the entities and how those entities are related in your database. Then you need to create a logical model out of it. So in the logical model is where you need to choose what kind of database management system you want to use. So if you want to use some sort of a relational database management system, then you can do the relational model of it, where you are going to find out what are the relations, or the more colloquial time of relations, are tables. So what are the tables you want? What are the attributes that you can put in each of the tables? What are the primary keys and candidate keys for each table? What is the foreign key for each table, and how those tables are related to each other? Now, after you have done the logical design, that is, after you have created that, what are the tables you need and what are the attributes that you're going to have in each table and how those tables are going to be related to each other. The next step that we need to do is we need to refine the schema. So the term schema essentially means description of the data. So when you are creating the tables, when you have created the tables and you have decided the primary keys, the foreign keys to decide how those tables are all interrelated with each other, we now, so that whole process or that whole diagram is known as the schema, which describes how the data is actually going to reside into your database. Now, after you've decided the schema, you need to refine the schema to ensure two main things. First, you need to ensure that there are as less number of redundancies as possible. Redundancies means duplicate data essentially. So you need to ensure that the data that you are keeping, that data is not getting duplicated in the kind of schema that you have created. And the second thing that you need to take care of is that you need to remove the anomalies as much as possible. So anomalies are actually caused when there is a lot of redundancies in the table. So that is when there's a lot of foreign key violation or when there is a data inconsistency. For example, if a data is duplicated into multiple places and you're trying to update that piece of data and you update the data in only, let's say 50% of the places and the other 50% of the places you do not update the data, then this causes an anomaly in the system. It causes a data inconsistency in the system. So your schema refinement is all targeted towards removing the redundancies and removing as much of anomalies as possible. So the process for schema refinement is mainly done using normalization, especially if you're using a relational database management system. If you're not using a relational database management system, there are other processes of schema refinement, which is out of scope for this particular talk. So we will be looking into normalization. But before we look into normalization and decomposition as tools, we need to understand a little bit of some more theoretical terms. So first thing that we need to understand is about something called functional dependency. So again, functional dependency is again a very important thing, which is actually decided when you are analyzing the data and when you are talking to the domain experts, to the business people to understand how exactly the data is correlated with each other. So what functional dependency essentially says is that if a collection of attributes is completely dependent on another attribute, that is based on the value of, let's say, one attribute, I can tell you what the other attributes will be. Then we say that there is a functional dependency between these two attributes. So if I have one attribute, let's say A1, and based on the values of A1 in a given table, and by the way, when I'm talking about these attributes, I am within the context of a single table. So in one table, whatever table that you have designed, if you've got one attribute called A1, and based on the value of A1, the other attributes, let's say A2, A3, and A4 are determined, then we can say that A1 functionally determines A2, A3, and A4. I can call it in the reverse way also, where I can say attributes A2, A3, A4 are functionally determined by the value of A1. So take a look into that example. Let's assume I've got a table like this, which contains the roll number, name, and the CGPA. Now here, I can say that the roll number determines the name and the CGPA of the student. That is, if I can give you that the roll number, if I can give you, you know what, I want roll number 3. So just by getting the roll number, can I tell you what is the name of the student and what is the CGPA of the student? The answer is yes, I can do it. That because roll number is something which is unique in nature, right? That every time a student joins a particular class or joins a university, I'm giving that student a unique roll number. So if someone gives me the roll number, I can always figure out what is the name of the student and what is the CGPA of the student. Now let us try to reverse the situation and let us try to see, can I make name also determine the CGPA and the roll number? So if I give a name called Pratik Bhattacharya and can I say that, hey, what is the CGPA of Pratik Bhattacharya? Now you may be tempted to think, yes, you can do that. If I go to the university and I tell, okay, this is the name of the student and give me the CGPA of the student, probably I'll be able to do that. But think of a situation where there are two students in that university having the same name. Like for example, let's say Pratik Bhattacharya. Let's say there are two students in the university whose name is Pratik Bhattacharya. So now if you go and ask the registrar of the particular university, give me the CGPA of Pratik Bhattacharya, they might say, which one? I have, let's say, 2 or 3 Pratik Bhattacharyas registered in the university at the same time. Whose CGPA do you want? Now, name is not a unique field. There are multiple students who can share the same name. So hence, name cannot functionally determine the value of CGPA. Because one name, there can be multiple CGPAs. So just by giving a single name, I cannot say, okay, this is going to be the CGPA. That might be possible in, let's say, 90% of the situations where, let's say, the names are unique. But there is always a possibility that there are 2 or more students having the same name. Hence, name cannot be used to functionally determine CGPA or the roll number. But roll number being a unique thing, which is actually uniquely added, given to every student who is joining that university. Using the roll number, I can always figure out what is the name and what is the CGPA. So roll number functionally determines both name and CGPA. So this is what is meant by functional dependency. Now, one thing which is very critical about functional dependency is that although from a perspective of common sense, probably as soon as you look into a table, you will be able to determine, okay, these are all the functional dependencies that you have. Like for example, roll number determines name and CGPA. But functional dependency is not something which is inferred. It is something which is already defined by the business. This is a business rule. See, the reason why I can tell you that the roll number uniquely can identify the name and CGPA of the student is because there is a business rule, or there is a rule in the university which says that every time a student joins, we are going to give the student a unique roll number. Because of the existence of this rule, I can say that the roll number can functionally determine name and the CGPA. Had this business rule not been there, had this business rule been non-existent, I couldn't have simply written a functional dependency called roll number will determine name and CGPA. So for functional dependencies, we need to talk, like as a developer, you need to get your assumptions, or rather you need to get your information from the business experts, from the domain experts who are actually giving you the requirements for building a table. You need to go back to them to understand what are the functional dependencies that you have in your system. Now, let me just, in this particular example only with this roll number, name and CGPA, let's add a trick to it. Let's add a twist to it. So here, let's say the university says that every time a student joins, we're going to give them the roll number based on the department that they belong to. Which means if you belong to the CSE department, you will have a unique roll number. All the students in CSE department will have a unique roll number. But two students picked up, one from CSE department and one from the biotechnology department, they may have different roll number. They may have the same roll number. Because here we are saying that the roll numbers are decided based on the department that you belong to. So in this situation, had that been the business rule, had the university been operating on this kind of a model, in this scenario, I couldn't have said that roll number alone determines name and CGPA. I had to say that roll number and the department code determines name and CGPA. So here you see, just by changing the business rule a little bit, our functional dependencies are changing. Hence, just by looking into the table, you cannot determine or you cannot infer what are the functional dependencies. You need to get your assumptions cleared by the domain experts, by the people who are actually running that university or running that particular domain in which you are writing the software. So now that we know a little bit about functional dependency, we will take a look into something called the inference rules. So inference rules means that given a set of functional dependencies, can you infer other functional dependencies out of it? So these are like safe rules where if you're given one set of functional dependency, you can try to modify that a little bit, break that a little bit, and using that you can determine all the other functional dependencies that you have. Now this thing, like this, when I say that you can actually infer functional dependency from another functional dependency, this necessarily does not violate the previous statement which I made where I said that functional dependencies are not inferred but they are defined. It is not essentially violating this. Here it is saying you must have a parent functional dependency first. That you must have a functional dependency which is being told to you by the business expert. And then you can do some modification to it, or you can do some addition and subtraction to it, which will automatically give you the other functional dependencies out of it. But those new functional dependencies which you are forming out of the original functional dependency, these are not essentially new functional dependency. These are just a different form of the existing functional dependencies that you have. So these new functional dependencies, they are not going to be breaking any rule. They are not going to be breaking any domain. They are simply a different way of representing the original set of functional dependencies that you have got from your business experts. Okay, now we will not go into very details of all these inference rules. So there are 6 inference rules. So first one is reflexing, which is a very trivial inferencing rule. It says that if you have got a superset, and then that superset will always functionally determine the subset, which is obviously very simple. That means if you have got a role and name, role and name will always determine the name of a student. That is very, very simple. Because see, like based on the role and the name of the student, I can only determine what is the name of the student. This is actually a very trivial example. So iron one is a very trivial inference rule. Second one is augmentation. So augmentation says that if you've got a functional dependency says X determines Y, if you add the same attribute to both the side, to both the LHS and the RHS, then the functional dependency still holds. So if X determines Y, then XZ and YZ or YZ also determines is also functional determines function is functional dependent. So for example, if I say the role gives you the CGPA, I can also say that the role and the name will also give you CGPA and the name. Obviously, like this is pretty obvious in nature, right? That if I simply add another attribute towards the role, then obviously, and I say add the same attribute in the CGPA, they are actually pretty much same to each other, because this name thing actually gets cancelled out with each other, and the role is what is actually functionally determines CGPA. Next inference rule, and this is a very interesting rule, which says X determines Y and Y determines Z, then X will determine Z. So that's what transition works. So if the Y kind of you put Y kind of common here, and you can say X will determine Z. And to understand that, let us try to figure out a situation where you are keeping the roll number, department ID, and the department name in the same table. So based on the roll number of a student, the department ID of the student is determined. Obviously, like every student belongs to a particular department, and based on the, and if I give you the roll number, you will be able to tell me what is the department ID of that particular student. So I can say roll number determines department ID. Fair, and that's fair. Now let's look into the department ID and department name. Now department name is also determined by the department ID. That is, every department name has a unique ID. Like let's say I can say department ID 1 is computer science, department ID 2 is mechanical engineering, department ID 3 is metallurgical engineering. So based on the department ID, I can determine what is the name of that particular department. So I've got two functional dependencies here. Role gives department ID and department ID gives department name. Then I can say the role actually directly gives the department name, because that is true, right? Since using the role, you can identify the department ID of the student. Using the role, I can also determine the department name of the student, because the department ID essentially gives way to department name. So this is transitive dependency, where you take two dependencies. And by the way, be aware of this, that whenever we are talking about functional dependencies, we are always in the context of a single relation. That is, where in the context of a single table, not across tables. So it is not like this department name belongs to some other table. Department name, department ID, roll number, they all belong to the same table. Only when they belong to the same table will you be able to draw all these inference rules. Our second one is decomposition, which says if X determines YZ, then X will individually determine both Y and Z. So it is again same, like if based on the roll number, I can find out the name and CGPA of the student, then based on the roll number, I can always find out the name and the CGPA individually. Union is exactly the opposite of it. If X determines Y and X determines Z, then X will determine both Y and Z. Same thing, if roll number determines name and roll number determines CGPA, I can say roll number will determine name and CGPA together. Pseudo transitive, it's a little complicated, and first time when you see it, you might get a little confused. What it says, if X determines Y and WY determines Z, then this Y can actually be replaced by X. So YX determines Z. So these are what are known as the inference rules. Okay. Before I go again into understanding deep into normalization, I would like to take a look into the live chat to see if there are any questions. All right, there aren't any questions. Fine, we can go ahead then. All right, we'll go ahead with normalization now. So normalization is like the process where actually we are going to take a look into functional dependencies and the keys that are present in a particular table, and use that information to reduce the redundancies and anomalies that you have in the system. And redundancies, we know what it is. Redundancy is actually nothing but duplication in the system. So normalization is a process using which we're actually going to be trying to remove as many redundancies as possible in the system. That is we are going to break the schema. Whatever schema is presented to you, we are going to refine the schema. We are going to break the schema to ensure that in a given table, as less number of duplicates can occur, so that as less number of duplicates are present. And if you're reducing redundancy, you're always obviously reducing anomalies as well. Now, before we go into exactly each process of normalization, you need to understand that normalization has different levels. Like there is something called the first level of normalization. There is a second level of normalization. Like this, there are 6 levels of normalization, and each level of normalization makes the schema more refined. So if you're at the 4th level of normalization, that means you have made the schema more refined, more better than a schema which is only 2nd level normalized. So this is what is meant by the levels of the normalization. And every table you can normalize, and each table you can give a particular level, that this table has been normalized up to this level. Now the entire database, which is comprised of all these tables and the relationships between them, even they have a normal form. And the database's normal form is the lowest normal form of all the tables that is present in the database. For example, if you have 3 tables, the first one is 4th level normalized, second one is 3rd level normalized, and the third one is again, let's say, 2nd or 1st level normalized. Let's say 1st level normalized. Then the database is only 1st level normalized. Because although there are 2 tables which have got very high level of normalization, but there is one table which is very low level of normalization. So the entire normal form of the database is dependent on the lowest normal form of its table. Okay, we'll start with the first normal form, which is known as 1NF. So this is a very trivial form of normalization, which simply says that the domain of any attributes must be atomic in nature. That means if you are in a given table, every attribute must have single and simple values. It cannot have complicated double values. To take an example of it, let's say you've got the course table, and we have been told that every course is going to have 2 teachers teaching that course. We call them as, let's say, course lecturers. So if you now try to capture that information, then what is going to happen is you've got the course ID and the course name, which are atomic in nature, which is fine. But the course lecturers, you will end up having reference, or you will end up creating double values or more than one values. So this is when it actually violates the 1NF, because course lecturers is not an atomic value. It's a pretty complicated value. So the way to fix it is you break it down. So basically, in normalization, whenever we see, for every level of, every time we see normalization and we see that certain rule or something is actually violating a normal form, the best weapon that you have with yourself is actually breaking it down. Decomposing our existing table into multiple tables is the correct way, or is the best way to bring the normal form back. So here what we have done is, since we know that each course is taught by multiple lecturers, multiple teachers, so instead of keeping the teacher information in the course table, we have moved the teacher information into the teacher table. So let the teacher table contain the teacher information. And since one course is related to multiple teachers, what we can do is, in the course ID, we can maintain a course teacher bridge table. And what is a bridge table? Bridge tables are generally used to be a bridge between 2 tables which have got a many-to-many relationship. And this is a many-to-many relationship because one course can be taught by multiple lecturers and one teacher can teach multiple courses. So this is an M2N, a classic M2N relationship. So to solve an M2N relationship, we have already seen in the previous videos that the best course of action is to create a bridge table which will have a reference to the first table as well as a reference to the next table. Okay, so this is how you kind of solve 1NF. Next is the second normal form. So the philosophy behind second normal form is that you should be having independent and as small footprint of the primary key of the candidate key that you have. So what theoretically this says is that every non-key attribute must be fully functionally dependent on the key attributes. That is, there cannot be any partial dependencies on the key, and the key should be able to determine all the attributes independently or fully. So what it essentially means is, now we already know the concept that when you're talking about the key attributes, and that is when you're talking about the primary key, a primary key can consist of multiple attributes. That is possible. Like for example, if you look into the course teacher table here itself, this bridge table, both the course ID and the teacher ID are contributing towards the key attribute. Both of them are key attributes. Both of them are primary keys. So it is always possible that any table can have multiple attributes, and and all those attributes together, they are acting as the key attribute. Now, what this 2NF rule says is that if you have got a set of attributes like that, like let's say you have got A1 and A2, both of them are the key attributes. Then all the other non-key attributes that you have in the table, like let's say A3, A4, and A5, they must be dependent both on A1 and A2. They cannot be functionally determined individually by A1 or individually by A2. Or A3, A4, and A5, which are the non-key attributes in the table, must be functionally determined by both the attributes and not by any single of them. We'll try to see an example. So let's say I'm trying to again create a table where I'm going to be keeping the names of the student and the marks that each student has received in each course. So for that, I have to keep, let's say, the roll number of the student, the name of the student, the course ID that the student has taken, and how much marks that student has received in that particular course. So like this, I've kept that information here. Now here, let us try to figure out as to what are the dependencies, or what are the functional dependencies that you have in the system. So both role and course ID can act as the primary key, can act as a key attribute for this particular table. So both role and course ID is going to give you the student name, course ID, course name, and the marks. That is fine, but it's based on the role and the course only. You can figure out what is the marks that the student has received, what is the course name that the student has taken, and what is the name of the student. Okay, there won't be a course ID here. Sorry about that. Okay, However, one thing that we are missing here is student name does not depend on the course ID. See, course ID and roll number, they are both the key attributes. However, student name does not individually depend on the course ID. It only depends on the roll number. See, like one course, multiple students can take that course, right? So just by giving the course number, course ID, I cannot figure out who is the student who has undertaken that course. I need to know more information. That is, I also need to know what is the roll number, and then based on the roll number and the course ID, I can tell you, okay, this is the student. Or rather, just by based on the roll number, I can tell you what is the student. Student doesn't depend on course ID. Student can or depends only on the roll number. And the same thing happens with course name as well. Course name is not determined by the roll number, because this roll number is actually getting replicated. If you can see here, like one student has taken multiple courses. So just if I give you the roll number, I cannot tell you, okay, what is the course name? There will be multiple course names for a given roll number. But if I give you the course ID, then I can tell you, okay, this is the course, this is the course name. So the course name is again dependent only on the course ID. So what has happened here is these two relationships where I'm saying that the roll number functionally determines the student name and the course ID functionally determines the course name. These are the relations, or these are the functional dependencies which are violating your second normal form. Because here you are not having full dependency. You are not having full dependency on the primary key, that is role and course ID. You are having partial dependency on them. So what is the situation here? The situation here is that you again need to break it. And the way we are going to break it is that all the individual functional dependencies which are actually breaking the 2NF, we first break them into their own tables. That is, we take roll number to student name. We first move roll number and student name to its own table. Then we take course ID and course name and we move it to its another table. So from this table, we are breaking it down into two tables first. First, roll and student name has been moved to their own table. These two will be moved to their own table. Second, course ID and course name. So I've got the course ID here and course name. So these are the two things which are again going to be broken down into a different table. Now we are going to see whether there are any attributes left which were actually dependent on both the role and the course name ID. And the value marks, this table, this attribute marks was dependent both on the roll number and the course ID. See, because if I just give you the course, I can't tell you what is the marks because I don't know which student I'm talking about. And again, if I just give you the roll number, I cannot tell you how much marks has been received because I need to know for which subject I'm talking about. So as a result of which, I need both the student roll number and the course ID to determine marks. So for any such relationship which is still dependent on both the attributes, we again create another bridge table out of it. Let us see it in action. It will be easy to. So first I say role and student name and course ID and course name. That has been broken down. So here it is role and student name, course ID and the course name. And then marks was another attribute which was dependent on both role and course ID. So we kind of create a bridge table out of it where marks will be dependent on both role and course ID. So now here you can see for the first table, role is dependent on student name. So that it doesn't violate 2NF, complete dependency. Course ID determines course name, does not violate 2NF because that's a full dependency. Role and course number gives you back marks, which is again not violating 2NF because marks have to be functionally dependent on both the roll number and the course ID. It does not have individual dependency. And here, if you see how we are reducing the dependency or redundancy, so you can see here roll number was getting repeated. Similarly, course would also be repeated because see there will be other students who would have taken the same course. So both course ID, course names, role, student name, they are all getting repeated in this particular table. But here, if you see that since we have broken it down, we have refined it into further granular forms, that kind of redundancy is completely gone. So here you see that the student, there will be no dependency, there will be no redundancy in the student table, neither will be there any redundancy in the course table, nor will be there any dependencies on the role, course, and the marks table. So this is one of the ways how using 2NF we actually reduce dependency. And one more thing was, as I said, that the philosophy of 2NF is always to have independent and good primary keys. So one trick that we generally follow in industry as well, that if you see the reason as to why here the violation of 2NF and everything was occurring is because in one table, in a big table, we're trying to create two attributes as a primary key. So if I say that, hey, and that is the reason why there was even a source, since there were multiple attributes, that is why there was this chances of, having, partial dependencies and stuff like that. So here, if I say that I'm going to remove the concept of having multiple attributes as primary key, and I am always going to be keeping a single attribute, and that single attribute is always going to act as a primary key, that should actually solve most of my 2NF concerns. Because if there is only one single attribute which is acting as a primary key, there is no chance of a partial dependency. All the other non-key attributes must be determined only one on that single attribute. So that is exactly what we have done here, right? when we broke it down into two such tables which has got a single attribute, a single key attribute. However, when there is no when we are creating bridge tables where actually both these two codes and student is needed, at that point of time we can create a bridge table which will have two keys as a primary key. So only in the situation when you're creating a bridge table, it is acceptable to have multiple attributes. But in other tables, if you simply say that I'm always going to be following a single attributes, that in 99% of the scenarios is always going to be in accordance with the second normal form rules. Going into third normal form, so third normal form says there should not be any transitive dependencies. That is, whatever non-key attributes that you have in the system, they must be dependent on the key attribute. That is true, but they should not be interdependent on each other as well. There should not be any dependencies where I say, attribute A4. So let's say I've got 4 attributes, A1, A2, A3, and A4. And I'm saying A1 is the key attribute. And A2, A3, A4, they're all functionally determined by A1, which is fine. However, there is some dependency where I say, but A4 is still dependent on A3 as well. So yeah, A4 is dependent on A1, which is fine. But A4 is also determined on A3 as well. So some of the non-key attributes that we have, there are some interdependencies among each other. Third normal form says you need to get rid of all this. Get rid of any transitive dependencies that you have in the system, and all non-key attributes must be completely determined on the key attribute. Let's take an example again. So again, this is our old example where I've kept the department and the student in the same table. So here you can see I've got the roll number and the department ID, and roll number and the department ID. Roll number is a primary key that you have here. So based on the roll number, I can find out the department ID. Based on the roll number, I can find out the CGPA. I can also find out the student name. And based on the roll number, I can also find out what is the name of the department, or rather in this case, what is the code of the department. So hence role functionally determines department ID, student name, CGPA, and department code. That is fine. That is good. However, let us try to analyze one of the dependencies that you have here. Is that role is functionally determining department code. Now, is that a direct dependency, or do you think this is actually a transitive dependencies? Now, if we go into the inference rules for a moment, we have tried to solve the same problem here. That is, I'm saying if roll number and department IDs are related with each other, that is, roll number is obviously going to tell you what is the student's department ID. And department ID actually tells you what is the department name. The department name is actually dependent on the department ID. And since department ID is also determined by the roll number, based on transitive rules, I can say that roll number is determining the department name. The same thing is actually happening here. The reason why we can say that the roll number functionally determines department code is because roll number is actually determines the department ID. Department ID determines the department code, and based on the rule of transition, I am saying that roll number also determines the department code. Hence, there is a transitive dependency in the table. That is, although that all these non-key attributes are dependent on the roll number, there is a non-key attribute which has got a transitive, or which has got a dependency on another non-key attribute. Department ID is not the primary key in this table, right? Roll number is the primary key in this table. So everyone is determined on the roll number, but department code is not only dependent on the roll number, but it is also dependent on the department ID. Or rather, a right way of saying that would be department code is indirectly dependent on the roll number by the virtue of IR3, that is a transitive rule, but department code is directly dependent on the department ID. So this rule, where department ID gives you the department code, this is the one that violates the 3NF. Now here is the question. So how do we solve it? Again, as I said, for any normalization problem, whenever you're trying to make a table fall under all the in the normal form, what you need to do is you need to again break it down. You need to again decompose the relationship. So that's what you're going to do. We're going to decompose the relation. And how we're going to decompose the relation? Again, the functional dependency which is actually violating 3NF, try to create a new table out of it. So move department ID and department code into a new table. So let us see if we can do that. Here it is. We have done that. We have kept roll number, student name, CGPA, and department ID in the same table, but we have moved department ID and department code in a different table. Now you can see for this table, roll number is student name, CGPA, and department ID, and there are no transitive dependencies in the non-key attributes. And in this table, department ID functionally determines department code, and since it's a separate table altogether, so yeah, this also is not violating 3NF or anything at any place. So this one becomes a 3NF thing. Now, however, one thing you need to be very careful about, and we will look into this when we actually look into decomposition rules. Department ID should be present in both the tables, because if you remove department ID from this table, then you will lose reference to the original data. So that's the reason department ID must remain in that table. And department ID was anyway like dependent on the roll number, right? So this was not causing any violation. So you can keep department ID here, right? And now, so there are other forms of normalization as well. Like we did only till 3NF. There are other for normalization, like fourth normal form, which is known as the Boy Scout normal form, which is nothing but a more, a more stricter version of 3NF. Then you have got the fifth normal form, which is dependent on multi-value dependencies. You have got the sixth normal form, which talks about multi-value joins and everything. However, we generally, or rather it is an industry-wide accepted phenomena that if your database is 3NF, that is all the tables that you have in your databases, they are at least 3NF or above, you are in good shape. You do not need to go ahead and do other form of normalization. So let us just understand a little bit about normalization. So decomposition. So we just saw that decomposition is the tool using which normalization is achieved. That is, every time we take a big table and we break it down into fine-grained multiple tables, we are actually decomposing the original table. So normalization is basically achieved via decomposition. So when you're decomposing, you need to so there are two rules that you need to understand, that you need to always follow. First one is your decomposition must be a lossless decomposition, and the second thing is your decomposition must preserve all the dependencies. Let's understand what is lossless. Lossless means there should not be any loss in data. So whatever relations that you have broken down into, if you join those relations once more, you're going to get back the original data. So if you've taken a table and broken it down into n different number of tables in the name of normalization, you can take all those n different tables, do an inner join between all those tables based on some attributes, and that is going to give you back that original data. To take an example, we look into this guy. So we took this information, broke it down into 3 different tables. Now, what if I have to write an inner join? How do I write? I will write an inner join between this table and this table, taking the roll number as a common attribute. Then I'm going to be doing an inner join on this table and this table, taking ports ID as the common attribute. So if we actually do that inner join, the information, the data that I'm going to get is going to be equivalent to this data. That is, I'm going to get back the original table. So that means there is no data loss. Similar thing is happening here as well. When I'm breaking down, or when I'm taking the department ID and the department code out, I can still do an inner join between these two tables. And if I do a proper inner join between these two tables, I'll still be able to get back the original data. That is, I'll be able to get back this table that you have here. But now, when I was doing the decomposition, what would have happened had I removed the department ID? That is, had I not kept the department ID in this table? Let's see what would have happened. So if I remove department ID from this table, your department ID is going to go back from here. So this is still in following 3NF because the roll number is giving you student and CGPA. So yeah, so there it is fully dependent on the key attribute, and there is no transitive dependency. So it is following both 2NF and 3NF. And department ID is giving me department code in this table. So this is also following 2NF and 3NF. However, how would I join this to table back? That is, if I want to get this information, that is, which student has received mark. The student is belonging to which department. I won't be able to get that information now, right? Because there is no way to correlate these two tables anymore. That's the reason why keeping the department ID was so important here. So had I not kept the department ID here, that means I would have had some loss of information. That is, I wouldn't have been able to get back which student belongs to which department anymore. So that would have been known as a lossy decomposition. But here, to ensure that we don't have a lossy decomposition and our decomposition is lossless in nature, we are keeping a department ID which will act as a foreign key and will reference the department table from the student table. That is what is known as the lossless decomposition. Dependency preservation. So this means that no functional dependency should be removed or new one should be created as a result of decomposition. So you already discussed about this, that functional dependency is business determined. That is, your business experts, they are going to tell you what are the attributes and how are they dependent on each other. So that's a business rule. So if you are removing a functional dependency from your database, that means you are actually violating the business rule. You are not writing a proper database. That is, your database is not reflecting how the rules of that particular university should happen. So if you try, so when you're trying to decompose, when you're trying to break your relationship, if you see that one of the existing functional dependency is not there anymore, that means you should not be doing it. So functional dependency, so dependency preservation means that no new functional dependency should be removed. So sorry, no existing functional dependency should be removed, and neither should new ones be created as a result of your decomposition. And basically, this is one of the reasons as to why a lot of people fret in doing 4NF, that is Boy Scout normal form. Because when you're doing Boy Scout normal form, what happens is that some of the functional dependencies do get removed. redundancies get removed. Like if like more normal form that you create, the better it is, because the more number of redundancies are gone. But your functional dependencies are also not preserved. So as a general, the thumb rule is that it is okay to have some redundancies in the table as long as you're preserving all the dependencies. So that's the reason why a lot of times after you've taken to 3NF, you generally don't have to go to 4NF, because that might cause loss of dependency preservation. Okay, before I end this session, I'd just like to talk about some of the from the industry tips. Like generally, so schema refinement is obviously critical, and schema refinement, like this is not a very theoretical topic. Like this is, although yeah, this topic is theoretical in nature, but this is not a strict academic process. Every industry must do schema refinement, and especially if they're doing an relational database management system, where the main purpose is to reduce or remove or minimize the number of redundancies that you have in the system and minimize the chances of having data inconsistencies in the system. You need to do schema refinement, and it is critical. And one thing that we need to understand is schema refinement must happen before your application goes live. Before you can actually release your application to the general public, you have to do schema refinement before that. And why is it? So let's say that you have got a schema like this. There is a huge table here where it is not following 2NF, it is violating 2NF. And now we need to break this schema into this kind of a thing. So when you are actually breaking the table, you're looking into the existing data, and then you're moving that existing data into these new tables. So what will happen when you're moving your existing table? A new record comes in. Like for example, let's say a new student is getting, like let's say you're doing some maintenance activity on the database, and you are actually breaking down this table, and you're breaking down this table into this new format. At that point of time, if a new student record has to be inserted, it is going to be a problem, because it cannot be inserted in this table, because this table is already getting broken down. And it may not be, and you may not be able to insert it in this table, because all the commands to insert it in the new format, they may not be ready yet. So in that situation, what you have to do is you have to kind of tell your business saying that, hey, I'm going to have a downtime that is for 4 hours. Your application is not going to work because I'm actually breaking down the database so that we can achieve second normal form or third normal form, or whatever it is. Now, this is actually not acceptable. That is, having downtime is not acceptable in all kind of products. Like for example, let's say you're using Gmail, and Gmail tomorrow comes up and tell you for the next 5 hours you will not be able to send any mails or receive any mails in Gmail, because we are breaking down our database to follow second normal form. That is not accepted, right? There is going to be a global outage. A global rage is certainly going to happen if something happens like that. That is the reason why doing schema refinement after the production goes live can have severe concerns, and that might have data losses. It might cause software downtime and stuff like that. Hence, schema refinement must be done before your production goes live. Just by looking into the data, you should be able to properly granularize the schema to ensure that you have got least chances of redundancies and inconsistencies. And another thing about the industry is that 3NF is widely accepted. As I said, that anything lower than 3NF is not accepted. But if you go above 3NF also, that is okay. But as long as you go till 3NF, that is going to be widely accepted by most of the industry that you have. And another quick tip about this normalization and the rules. So I know that when I was talking about 2NF and 3NF, I was giving a lot of academic knowledge there, like how you should be looking into transitive dependencies, or how you should be looking into partial dependencies and stuff like that. Generally, when you're in the industry, you do not get to apply such theoretical knowledge, or rather although the theoretical knowledge is very much applicable, it is not a bogus knowledge that I'm giving you. Those knowledge are very applicable. But however, you may not always be in a setting to actually go ahead and apply those theoretical knowledge of partial dependency, transitive dependencies, and all those stuff like that. So what generally happens is that whenever we have defined the schema, we try to look into whether, given this particular schema of a table, whether there is some chance of having redundancy, having some chance of data duplication in the table. If there is a chance of having data duplication in the table, that means we have done something wrong, and we need to break this table down. This is the mantra, that if you see that the table that you have created, the table that you have designed, the schema that you have designed, when you actually try to enter data into the table, there will be duplicates into the table. You have done something wrong, and you need to break it down immediately. So this is generally the mantra that we follow. And when we have done that, when you have, let's say, come up with a schema where there is very less chances of redundancies, it is 99% probable that you have already achieved 3NF. So when you are trying to achieve normalization, obviously after after you have done the schema refinement, you need to get it reviewed by your data architects and senior engineers who are actually going to be seeing whether it is truly following 3NF or whether it is following 2NF and stuff like that. But however, intuition plays a huge part in actually normalization. Like not everything can be actually done in a theoretical knowledge, especially when you're looking at some complicated data sets and everything. So you need to use a lot of your intuition into understanding wherever you see redundancies, wherever you see data duplication, you have done something wrong, and probably you need to break down this. All right, so that's it for today's session. I'm just going to take a quick peek with as to whether there are any questions on the live chat. Okay, how will we identify what table is in which normal form? That is a question that is given by Harsh. So yeah, so the answer to that question is that how you're going to determine is, so first is that if you're trying to determine 1F, you need to 1NF, you need to understand that if you need to see whether your table all the values are atomic or not. If all the values in your tables are atomic, then you can safely say this table is 1NF. Second thing is, for 2NF, you need to take a look at whether all the dependencies that you have in your system, all the functional dependencies that you have in your system, which have been defined by your business, whether they have any partial dependencies or not, or whether they are completely dependent on the key attribute. Now, if I go ahead and actually tell you the tips and tricks that I told you, that if you actually create a table which has got only one primary key, you will always be in second normal form. So that's the tips that we see. So if I've created a table where there is only a single primary key attribute, I am 100% sure that this is always going to be in 2NF. It is only the bridge tables when I need to take a relook at it, that if there are two primary keys, whether all the other non-key attributes have complete dependency on them or not. So that is how you check 2NF. And for 3NF, yes, again, 3NF also the best way to check for that is, so if you see that every non-key attributes are dependent on a particular key attribute, but there is a chance that there is a functional dependency which has been told to you by your business, and you see that that functional dependency exists in this table between two non-key attributes, that means you're doing something wrong here. So again, these are all again very theoretical knowledge. The most practical knowledge is every time you see there is a duplication or there is data duplication in your table, you should understand it is not in the normal form, and you should break it down to bring it into some of the normal forms. So that's the kind of the tips and tricks that you can see. Okay, I think there is another question here, which is again by Harsh. What kind of questions can be asked in interviews related to normalization? So a lot of times, a lot of practical questions are actually asked into the system, where actually you are literally given a lot of records. You are actually told, hey, so let's say that you are trying to design the database for Amazon, and you are actually told, okay, design the relational database for Amazon. So when you're doing the database design for Amazon, after you've done the database design, after you've created the tables and how those tables are going to be related to each other, you will be asked, to which normal form did you consider? Did you consider 2NF? Did you consider 3NF? Did you consider 4NF? If not, why? So all these kind of questions will be asked. A lot of practical scenario based questions are actually asked. And then if you say that you have past experience, if you have prior experience in designing databases, then also you will be asked that to which normal form did you consider your database to be, and how did you determine that it was of that particular normal form. So this kind of questions are asked, so especially if you're going into a company which does a lot of work on SQL and stuff like that, you can expect you can definitely expect questions on normalizations. All right, I don't think there are any questions. And as I said, that if there are any further questions, you can always put that question in the comment section, or you can put that question if you in the discussion forums if you have registered for that course from Newton School site. With that, I'd like to thank everyone for joining the sessions. I do hope that you got to learn something from this session. So till we meet next time, and the next time that we meet in the next video, we'll be looking into some more advanced concepts. Especially, we'll be looking into something known as group by queries, and we'll also be looking into indexing and hashing. We'll be looking into some of the concepts of how that is important in a database world. All right. Thank you, everyone. And once again, have a good day.